Okay, so last week we talked about comparing two samples, taking two samples and using them to make inferences about their respective means. Okay, their respective populations and the means of those populations. Okay, so we did. We saw two samples, and we used the samples. We created a confidence interval from the samples for mu1 minus mu2, which was the basically what we believe to be the difference between the mean of population 1 and the mean of population 2. Okay, so and from this confidence interval, depending on the confidence interval, we could conclude whether or not there was evidence for a difference between the means of the populations. Okay, and so if the confidence interval contained 0, then that means we didn't have evidence that there was a difference between the population means. And if the confidence interval did not contain 0, so it was entirely positive or entirely negative, then we had evidence that the population means were different. We could say whether or not and I said this was our first introduction to inference. Okay. So this was our first or exposure to inference. Okay, which is about taking data that we observe and from that inferring about the populations from which they came. Alright, so today we're going to introduce another method of inference, okay? And it's basically doing something very, very similar to creating a confidence interval, but it's coming from a different perspective, okay? So with the confidence interval, it's like, I see data here and I see data here, and let's use what we understand about sampling distributions to kind of see what the data say. This week and actually most of the other inference methods go off of something called a hypothesis test. Okay, we're going to learn about hypothesis testing. And the first hypothesis test we're going to learn is going to be using data to compare population means. Okay, so it's very similar to confidence intervals, but it's going to have a very different feel in terms of the process that we go through. And the idea behind a hypothesis test is we set up a hypothesis called the null hypothesis. And either the null hypothesis is true or it's not. Okay? And then we look at our data. And then we say, well, let's assume the null hypothesis is true. If it's true, what is the probability that I would observe my data? Okay, so let's let me just create a hypothesis. Okay, and this is called the null hypothesis. And the null hypothesis is either true or it's not, okay? And if it's not true, we call that the alternative hypothesis, okay? The possibility that it's not true. If the null hypothesis is not true, then the alternative hypothesis must be true. Okay, so and we call this a hypothesis test because we're testing to see whether or not the null hypothesis could be true, whether or not it could be true. Could the null hypothesis be true? Okay, so to test it, we look at data. And we ask the question, if the null hypothesis were true, what is the probability of observing data like ours? Okay, and I'm going to put a little star. The asterisk says, or something more extreme. All right. I don't. This is so abstract right now. I'm not even sure if this makes any sense to you guys at this moment. But I'll ask a question, and maybe it does make sense or not. Okay. So again, basically we're just making some kind of statement about that could be true or not. Okay, some kind of statement, and then we're saying, okay, well, if that statement is true, if that null hypothesis is true, what's the probability of observing this data that we have right here? So we actually observe this data, and we say, what's the probability of observing this? Okay. If we're hoping the null hypothesis is true, would we want that probability of observing our data to be high or low? We want it to be high. Okay. And if it's low, then it provides evidence that maybe our null hypothesis is not true. Okay. So maybe I'll try this with an example. Okay, so a non-statistics example, but a little bit of probability involved. This is an example. Okay, so I went to Las Vegas last week, and okay, so let's say I played a game. All right, I played a game a bunch of times, and let's say you know, I win, and I win several times in a row or whatever, or I win more than what you think I should. And then so the pit boss or the casino managers, they come up to me and they say, we think you're cheating, okay? And I'm gonna say, oh no, I'm not cheating, right? Okay. So now, so are you guys familiar with the game roulette? Okay, so in roulette, you can bet on, there's 36 numbers plus 2 more, so 38 numbers, and anytime you correctly guess one of those numbers, they pay you 36 times whatever you bet. Or there's 2 colors, there's red and black, and then there's also the greens. But anytime, and about half of them, almost half are red and almost half are black. And so if you choose red and it lands on red, then they pay you even money. So if you bet $10 and on red and it lands on red, then they'll give you $10. Okay, so you have almost a 50% chance of winning. Okay, it's not quite, because the casino has rigged not rigged all the games, but set up the games in such a way that where they're always the expected values that they're going to be earning some money. Okay, but let's say I'm just playing roulette and I'm just betting on red. Okay, so then I should be winning about half the time, maybe a little bit less than half the time if I play a whole bunch of times. Okay, let's say I play 10 games, and rather than winning 5 out of 10 or 4 out of 10 games, let's say I win 8 games out of 10. 8 games out of 10. Okay, and then the casino says, "You're winning too much. We think you're cheating." Would you say this is evidence that I'm cheating if I win 8 games out of 10? No, we would not. We would say 8 games out of 10, that's not evidence of cheating. So I won 80% of the time there. For whatever reason, we're saying that's not enough. Okay, but let's say I play 100 games and I win 80 of those games. So I'm still winning 80% of the time. If I win 80 of those games out of 100 games, and the casino says, "We think you're cheating," would you agree with them, or would you say, "No, he's just lucky"? I think nobody?
You're a cheater.
I'm a cheater. Okay, so if I win 80 out of 100, then that makes us uncomfortable, and we're saying he's probably cheating. Okay, he's probably cheating. Okay, maybe he's just super lucky, but he's probably cheating. Okay, and certainly if I play 1,000 games and I win 800 games, then they would come and break my legs or something, right? They would say, "Certainly you are cheating." Okay, now in all of these situations, I'm winning 80% of the time. Okay, and the only thing that has changed is I played 10 versus 100 versus 1,000 or something like that. Okay, so why is it that when I play only 10 games, we would say, we're not going to outright and say you're cheating, but then if we played 1,000 games and I win 80% of the time, then you would say I'm cheating. What's going on there? Okay, well, let's set this up here. Okay, so example. Okay, so we're gonna play roulette at the casino. Okay, and then I'm accused of cheating. Okay, so they accuse me of cheating. All right, so I'm going to set up a null hypothesis. Okay, the null hypothesis or we call this H naught, H0. Okay. The null hypothesis is I am not cheating. Okay. And the alternative is that I am cheating. So if the null isn't true, then the alternative must be true. Okay, I should say cheating at roulette. if the null hypothesis is true, then my probability of winning, if I'm just betting on red, would be 16 out of 38, okay? At least in a United States casino. Okay, so I would have a 42%, is that right? No, 18 out of 38, sorry. 18 out of 38, I would have a 47% chance, 47.4% chance of winning. Okay, so then, so probability of winning on red would equal 0.474. Okay, so that if the null hypothesis is true, then this must be true, right? If I'm not cheating, then my probability of winning on red would be 0.474. And the implication is that if I see anything, that any of my data, any of my winnings, whether I win or lose, is just a result of pure random chance, okay? My wins and losses are a result of pure random chance. The alternative is that my wins and losses are no longer just a result of chance and only chance, but rather my wins and losses are a result of random chance plus the fact that I'm cheating and I've manipulated my probability of winning to be higher than 0.474. Okay, so the null hypothesis is that I'm not cheating at roulette, and that implies these other things. That my probability of winning is what it should be, and that what my wins and losses are just a result of chance, or random chance. Okay, the alternative is that that my wins and losses are a result of random chance plus something else that increases my probability of winning. So we would say probability of winning on red is greater than 0.474. Okay? We don't know what it is, but we're just saying if I'm cheating, then I've done something so that my probability of winning on red is higher than 0.474. Okay. Does that make sense? Okay, so this is what we've set up in our heads. And so this is how the hypothesis test would go. So scenario 1, okay, play 10 games. Here, well let's just start off with the simplest of scenarios. Okay. Okay, so if I play 5 games and I win 4 of them. We would say that's pretty lucky, right? That's pretty lucky. And we could say the way we test our hypothesis, okay, we're going to say let's assume the null hypothesis is true. Okay, so this is the evidence presented, right? The casino, they take me to casino court and they say, we believe you are cheating. And I say, okay, what's the evidence? And they say, well, you played 5 games and you won 4 games. That's 80%. So you won 80% of the time, which is more than 0.474. Okay. And I say, okay, well, in my defense, let's assume H0 is true. Okay, let's assume the null hypothesis is true. Then we ask, if, just for argument's sake, let's say I'm not cheating, what's the probability that a non-cheater just happens to win 4 games out of 5? A non-cheater who wins 4 games out of 5, because just from being lucky. Okay, or just from random chance. Can we answer this question? This would be a binomial problem, right? Binomial, and we would answer this question, and we would say 5 choose 4, 0.474 raised to the 4th, and 1 minus 0.474, which is 0.526 raised to the 1. Okay, this would be the probability of winning exactly 4 out of 5 games. Okay? Now the asterisk is that our data or something more extreme. Okay, and so in this case, more extreme would be winning 4 games out of 5 or 5 games out of 5, right? If the casino comes and accuses me that I'm cheating because I won 4 out of 5 games, they would certainly accuse someone of cheating if they won 5 out of 5 games, right? So basically, we have to add any other situation where they would accuse someone of cheating. So we would say probability of winning 5 out of 5 games, which is just 474 to the 5th, but to follow our binomial form, we do that. Okay, I don't know. Does somebody have a number here? Let me see. 474 to 4 times 4. Okay, and I'm getting 0.157. I just punched this quickly on the calculator, so I don't know. Okay, so 0.157. Is that? I don't know. Someone can corroborate that. Okay, so if somebody was just playing games at the casino and they just kept betting red, there's almost a 16% chance that they play 5 games and they win 4 or more games. Okay. So there's a 1 in 6th chance this could happen just by randomness. So would we say we have evidence that I'm cheating, or we don't have evidence that I'm cheating? We don't have evidence that I'm cheating. Why? Okay. So the reasoning here is that this is the probability of observing our data or something more extreme if we assume the null hypothesis were true. Or in other words, if we assume that I'm not cheating. This probability is relatively high. Meaning it does not provide evidence that the null hypothesis is false. equivalent of null hypothesis false is that the alternative is true. So, oh, the alternative is abbreviated HA. Oh, I did put that there. The alternative is true. So it doesn't provide evidence that the alternative is true, or it doesn't provide evidence that the null hypothesis is false. Because this probability is relatively high, it just means we could observe whatever data we got just by random chance. All right. Does that make sense? Yes?
It's context to determine that that's
Yeah, we set an arbitrary line, okay? And actually the researcher can choose whatever level is going to be high or low, okay? I mean, 16% is not high, but it's certainly not low enough to just say you're cheating, right? If somebody says, watch this, I can do magic, I'm going to roll a die and it's going to land on 5, and then they roll a die and it lands on 5, you're not going to be, that's not going to be that impressive. You're just going to say, oh, you just got lucky, it landed on 5, right? Especially if you say, well, do it again, and they're like, no, I'm not going to do it again, right? No, one-time trick only. Then you're just going to say, no, you were just lucky, okay? So anyway, yeah, this arbitrary, whether it's high or not is up to you as a researcher, and we'll talk about it. The established number has been 5%, okay, through the literature, okay. This thing here, we give it a special name. It's called the p-value. You might have heard that if you've read some kind of research papers, but this is the p-value. This is the probability of observing our data, or something more extreme, if we assumed the null hypothesis were true. That is also known as the p-value. Okay, and we're going to repeatedly see the p-value for the rest of this class. Okay, this is classical statistical inference. Okay, today now there's Bayesian statistics is all the rage and stuff like that. And the p-values are less seen as less important or whatever, but p-values are still very much in use in all of classical statistics. So anyway, on the other hand, okay, so here let's keep talking about this. So if I play 4 games out of 5, it doesn't prove that I'm a cheater. Okay, that's not enough evidence for the casino to say you're a cheater. Okay, does it also prove that I'm clean, that I'm not cheating at all? No, it doesn't. It doesn't prove that I'm not cheating either. Okay, at this point, it just means you either got lucky and you won 4 out of 5 games, okay, and you're not cheating, or maybe you're cheating, but you're smart enough where you played only 5 games, so we can't pin it on you. Okay. So, even though this is high, and so it's not evidence to prove that the null hypothesis is false, but it also doesn't prove that the null hypothesis is true. Okay. So while we do not have evidence to prove that the null hypothesis is false, it also does not prove that the null hypothesis is true. Okay, and this is this concept. You know, when set up like this, it seems pretty clear that it doesn't prove that I'm not cheating either. But somehow, in a lot of research articles and things like that, or when people maybe a research article is published, but then somebody will read the research article and then write like a summary on it on some news website or blog or something like that. A lot of times they will incorrectly say that because we didn't reject the null hypothesis, because the null hypothesis wasn't proven false, they assume that the null hypothesis is true. That is not, you cannot do that, okay? With hypothesis testing, no matter what data you have, it will never prove the null hypothesis is true, okay? It just means you don't have evidence to reject the null hypothesis, okay? Or you don't have evidence to support the alternative hypothesis. So, in hypothesis testing, we can never prove that the null hypothesis is true. We can only use our data to prove against it. Okay. But if we, you know, if I played 100 games at the casino, and I win 80 games, the probability, okay, the probability of winning 80 games out of 100, if the p-value, not the p-value, if the probability, if the null hypothesis were true, if the probability of winning was truly 0.474, this probability of winning 80 or more is practically zero. Okay, we could do a normal approximation and things like that, but this probability is going to be practically zero. Okay, because so with 100 games, so with the normal approximation, my mean would be n times p. So I would expect to win, 47.4 games. My standard deviation is going to be about 5, I think. 0.474 times 0.526. So yeah, 4.99. So I'm just going to say 5. My standard deviation is 5. If I've won 80 games or more, and at 80, okay, so with a continuity correction, I would draw a cutoff at 79.5. Okay, my z-score at 79.5, 47.4 over 5. This is like, I got a z-score of 6 or something. .42. I've got a z-score of 6.4, 6.5. Okay. What's the probability of seeing a z-score 6 standard deviations away from the mean? It's like 1 in it's like 1 in a million. Okay, 1 in a million. So let's just say the probability of seeing this, so my p-value in this case would be, let's just say 1 in a million. So again, I'm in casino court, and they say, we think you're cheating. And I say, oh, what's your evidence against me? Well, you played 100 games betting on red, and you won 80 of those games. And we did the math, and the probability of that happening is 1 in a million. Okay? So my defense would be, oh, well, I'm just really, really, really lucky. Okay? And I guess that's possible, all right? It's possible that I just got really, really, really lucky and I happened to win 80 games out of 100. But more likely is that I was not this lucky, okay? I was not the lucky 1 in a million to win 80 games out of 100, but rather I have done something to increase my probability of winning. Okay, so with a p-value like this, okay, this says, okay, so if the null hypothesis were true, So if I'm not cheating, okay, the probability of winning, 80 games out of 100 is about 1 in a million. So I could say I'm just really, really lucky, or I think you're cheating, okay? So either I'm just very, very lucky, okay, or our assumption that the null hypothesis is true is wrong, okay? Or our assumption that I am not cheating is wrong. Okay. Is it possible that I was playing a fair game and won 80 games out of 100? It's possible. It's very, very, very unlikely, but it's possible, okay? But in that scenario, maybe the casino, they go and then they break my legs because they say, we think you're cheating, okay? Or we've got strong evidence that you're cheating. It's possible that I was being honest and I just happened to be so lucky that it became unlucky that I was the one in a million to win this, okay? But at some point we got to draw a line and say, you know what, it's so unlikely that we're just going to say it's not a result of random chance, but something else is happening, okay? And I think 1 in a million it's okay to say that, all right? So with other scenarios, you might not see probabilities or p-values that are so distinct, right? Maybe you see a p-value of 0.02, okay? So if, maybe somebody else played some other number of games, and the probability that, winning however many games they got by random chance is only 2%, okay? Do we say you're cheating, or do we say you're not cheating? Okay. Well, we have to make decisions at some point, okay? And so if something like that happens, all right, well, the casino, maybe they won't break your legs, but they might just say, you know what, please don't come back to our casino, okay? And they'll say, please don't play here anymore. And that way, they're willing to take this. There's a slight risk that they made a mistake, right? There's a 2% chance that this person won this many games just by pure luck, but they're willing to take that 2% chance and say, you know what, we'd rather just not have to deal with this person than have a cheater here or something. Okay, I don't know. Who knows? So anyway, this is how we set up our hypothesis tests. We set up a null hypothesis and an alternative, and then we take our data and we ask, what's the probability of observing our data if the null hypothesis were true? Yes, Marissa.
Does it affect the p-value if you're not the only one betting on red?
Well, it does not in terms of if we're only looking at the data. The data that we've gathered is the only thing that will determine your p-value. Or the null hypothesis and the data you've gathered are the only things that determine the p-value. Okay, so what other people are doing, if they're not brought into the equation here, it doesn't matter. Okay, it doesn't matter. All right. So anyway, this is just kind of my example to get us into the mindset of hypothesis testing, and from there we can look at the actual hypothesis tests that we set up when we look at data here. Okay, so all of the examples in chapter 7 are not casino examples, but they are they relate to something called the t-test. Okay, so starting with section 7.2, we learned something called the t-test. I'm sorry, I hate to do this to you guys. Okay. Let me just talk a little bit about section 7.1. Okay. 7.1 is trying to get this idea of what could happen by truly random chance. Okay. Okay, and this is they call, I don't know what they call this. The randomization test. Okay. And here, what they're doing is they're saying, okay, here we observed, so in all of these tests here, we're comparing, we observed 2 samples and we're comparing the means of these 2 samples. Okay, so in both 7.1 and 7.2, we observed 2 samples. And we compared the means of the 2 samples. Anytime you take 2 random samples, and this is now quantitative data, right? Our casino data was categorical, you won or lost, but now we're dealing with means, and so we've got quantitative numeric data. So anytime you take 2 samples of numeric data, even if they come from the same population, or if they come from different populations, whenever I take 2 samples, and I find the mean of this sample and the mean of this sample, there's almost certainly going to be some kind of difference, right? I take, let's say I take 10 random men and I average their weight, and I take another group of 10 random men and I average their weight. It's very unlikely that I'm going to get the exact same mean weight for these 2 samples. So we're going to observe some kind of difference. Okay, there will be a difference between the means of the samples. Okay, and that difference is y1 bar minus y2 bar. So if I pick 10 random men, okay, so let's say I pick 10 random men from California, 10 random men from Oregon. Let's say the average of these 10 random men in California is 165 pounds, and the average weight of these 10 random men from Oregon is 168 pounds. Okay, there's a 3-pound difference between these sample means. Is that 3-pound difference enough for me to say, oh, people in Oregon, the men in Oregon weigh more on average than the average weight? The average male weight of someone in Oregon is higher than the average male weight of someone from California. No, right? We'd say, oh, 3-pound difference, that's not much, okay? But in our brain, we've got something that says, oh, okay, well, a 3-pound difference between a group of 10 men and a group of 2 groups of 10 men does not seem like a big deal. Okay. On the other hand, if we've got 10 random men from California and 10 random men from some other place. Let's say there was some remote island, and we just discovered these people, and we picked 10 random men from this remote island, and they have an average weight of 130 pounds. Okay. Then would we say, oh, you know what? The men on these islands weigh less than the men from California? Probably, right? So something in our brain says, a 3-pound difference between two groups, not a big deal. A 30-pound difference between two groups, or the averages of two groups, seems like a big deal. Okay, just like, so there's something intuitive that we have going on, especially when it's coming to the weight of humans, which is something we're generally familiar with. Okay, but anytime you look at some other random data set, we want to know, is the difference that we observe, is this a big deal or not? Okay. Basically, is this observed difference So when we do the t-test, we're going to just ask, what's the probability of observing a difference like this, or something more extreme, if the null hypothesis is true? With the randomization test, we do the same, we ask the same question, you know, what's the probability of observing a difference like this, except we actually, physically, or not, I don't know. We randomize the data itself. We take the actual numbers that we gathered, and rather than saying these came from some population, we're going to just say, what if I just shuffled the data? Okay, so here I've got 10 men from California, 10 men from the island, and what if I took off the labels? You know, here's a 140-pound man from California, a 180-pound man from California, and so on and so forth. And I just said, here are 20 weights. And what if I just shuffled them up and I dealt them out into two piles? Okay. When I deal them out into two piles, we know that, okay, and I take the average weight of this pile and average weight of this pile, they're not going to be exactly the same. But we also know that the difference between the average weights is just a result of pure random chance, right? So I take the 20 weights, I shuffle them up, I deal them out into two piles, I find the average of pile 1, average of pile 2. Any difference I observe between these two piles is just a result of the random mixing up that I did, okay? And if I do this a whole bunch of times, or if I figure out every single possible arrangement of of putting 10 into pile 1 and 10 into pile 2, I could figure out whether or not the observed difference we got is something unusual or something mundane. Okay, so if I constantly shuffle these and I do this over and over and over again, and I'm repeatedly seeing differences of, you know, 2 pounds or 6 pounds, and like after doing this 1,000 times, maybe the biggest difference I saw was 15 pounds between the two random piles. When I see a difference of 30 pounds, I know, okay, that's rather unusual. Okay, or maybe the 30-pound difference happened only once out of 1,000. That's still rather unusual. Okay, but let's say there's the variety of all these people is so much that when I shuffle them out into two piles, you know, I get 30-pound differences like 10% of the time. In that case, we would say these 30-pound differences is not a big deal. I don't know if this made any sense. In my brain, I'm explaining this, and of course I understand it and it works, but okay, so, well, let me just write that up. So we observe two samples and we compare the means. There will be a difference between the means of the samples, y1 and y bar. Is this a big deal or not? Okay, so in the randomization test, we take all of our data points and mix them up. We deal out two piles. Okay. Pile 1, pile 2. And record difference between the mean of pile 1 and pile 2. And we repeat this many, many times. And by repeating this many times, we gain an understanding. By repeating this many times and observing all the differences that we see between pile 1 and pile 2. Excuse me, something, my throat just dried out. By doing this many times, we get an understanding of what kind of difference we should observe. Okay? We can get an understanding of whether or not a 5-pound difference, is that a big deal or is it not a big deal? Okay. Repeating this process, we can gain an understanding of what kind of differences okay. Is that okay? And when you use a computer to do this, so a lot of times people will use computers to do something like this because you don't actually want to take 20 data points and shuffle them up and deal them out. I mean, you can take a deck of cards and write all your data points and then shuffle them up and literally deal these out and see what happens. And that would actually be a very good, I think, learning activity. But normally we just do this on the computer, and we call this process bootstrapping. Okay, so when done on the computer, bootstrap, and that's just a very simplified version, or I guess maybe the most simple form of bootstrap. It's very useful. I don't know. Anybody heard that? Okay. All right. So anyway, we're not going to do this. Okay. We can, but we're not going to. Instead, what we do is we're going to do something called the t-test. Okay. And the t-test, it's still asking the exact same thing. This part up here, we observe 2 samples and we compare the means of the 2 samples, and there's some difference, y1 bar and y2 bar, and we want to know, is this observed difference a big deal or not? That part is exactly the same. The part that's different is that we're not going to say, I have no idea what the differences look like, let's shuffle this up many times and see what kind of differences we get. We're going to say, well, I understand a little bit about distributions and the normal distribution, and so I'm going to use my understanding of the normal distribution to decide whether or not this difference is unusual or not. Okay, we're going to say, we're going to take our understanding of the normal distribution, or technically the t-distribution, to decide whether or not some observed difference is unusual or not. Okay, so same setup as before, but now so what this means, so an implication of this is that it needs to be appropriate to assume the normal distribution or t-distribution. Okay, so an implication of using this to say, well, I'm going to use my understanding of the t-distribution or normal distribution to decide whether something is unusual or not. That means we need a situation where it's appropriate to use the t-distribution or normal distribution. Okay. So this means do you guys remember when it's appropriate to use the t-distribution when talking about means? T or normal distribution? Or I guess when does the central limit theorem apply? So the central limit theorem says that means of samples follow a normal model. A normal distribution. When does that happen?
When the sample's large.
When the sample is large and we're taking the mean, right? Or if the sample's not large, then the population is normal, okay, or close to normal. So the t-test is best when you've got a large samples or two large samples where you can assume that the mean follows a normal distribution, or you don't have any crazy outliers. So almost always for the t-test, our null hypothesis will be this. Is that the mean of population 1 is equal to the mean of population 2. Okay. Or alternatively, this is exactly the same thing, and a lot of times we will also write this. These two things say the same thing, right? So we're either saying the mean of population 1 is equal to the mean of population 2, or the difference between the means is 0. So they're the numbers are the same, or the difference between them is no difference. Okay, because they say the same thing. And then so the alternative is basically that the null is false. Okay, so in this case, we can have a few alternatives. Okay, one of the most common is that they are not equal to each other, but also other possibilities and conversely these all become and yes, you can have the null hypothesis state that the means are the same, and the alternative being that group 1 is bigger, or group 1 is smaller. It doesn't have to be, so the null is always going to have an equal sign. So that's also something to remember, okay? The null hypothesis will always have an equal sign. The alternatives can have not equal, greater than, or less than. Okay. And we use the greater than or less than when we're only interested in a certain direction, what we call a direction. Okay. So I'll also write that. Okay. So these two are known as directional. one-sided. And this one is non-directional or two-sided, two-tailed. Alternatives. So the alternatives are directional or non-directional or one-sided or two-sided. Okay, so let's try out an example. I'm gonna barely get this in time. Okay, so let's say I observed one sample. Sample 1, we've got some men, 10 random men, and the average, we'll say we measured their IQ. Okay, and we'll say, let's say the average IQ of these 10 random men was 102 with a standard deviation of 15 points. Okay, and let's say we took some women, let's say 12 women, and let's say the average IQ of these randomly chosen 12 women was 100 with a standard deviation of 14. Okay, and we want to know, is this evidence that men and women have different IQs? Okay. Now, so our null hypothesis would be men and women have the same IQ. And the alternative, okay, so, well, I'm going to be, forgive me for being verbose here, okay? Or same, not men and women have the same IQ, but same mean IQ, right? Any individual is not going to necessarily have the same, be the mean. So men and women have the same mean IQ. Any difference observed between samples is a result of the random selection. Or basically just the randomness and the picking of the sample. And then the alternative, so we can say mu1 does not equal mu2, or if someone was trying to prove that one group was smarter or had a higher IQ or lower IQ than the other, then we could put in a greater than or less than sign. Okay. And here this would say men and women do not have the same IQ, have same mean IQ. Rather, differences observed are a result of randomness plus some the fact that the means are actually different. Okay. Well, from here we'll say, okay, well, let's do our test. Okay. if the null hypothesis were true, what's the probability that I get a difference that I observe? So what is the observed difference that I saw? So my observed difference is y1 bar minus y2 bar. I observe a difference of 2 IQ points between the two samples. And I'm going to ask, well, if the null hypothesis were true, if the true difference between the mean IQ of a man and the mean IQ of a woman is 0, what is the probability that I take 20 random people, 10 random men and 10 random women, and I get a difference of 2? Take 2 samples and observe a difference of 2 or more. Okay. So if this probability is high, then what does that mean? So let's say I go through this process, and we're going to run out of time, so we're not going to go through the actual process of finding this thing. But let's say we go through this process, and the probability turns out to be 40%. What does that mean? Well, it means that there's a 40% chance that okay, so if men and women truly had the same mean IQ, there's a 40% chance that whenever I take 10 random men and 12 random women, I'm going to get a difference of 2 or more. Okay? That's going to happen 40% of the time just by randomness. So to me, that says I don't have evidence that men and women have different mean IQs. On the other hand, if we go through this process and the probability of observing 2 is like 1%, so the probability of observing a difference of difference of 2 IQ points or more is only 1%, then that means if men and women have the same IQ, anytime I take taking random groups, I'm only going to get a 2% difference like 1% of the time. That means it's pretty rare, and my data provides evidence that men and women don't have the same mean IQ. Are we following? Okay.
Wait, so for, say the probability is like at 1%, does that imply that it's a greater difference than 2 or less?
It just implies that my null hypothesis can't be true. Okay, or that it's unlikely that I would see this data just by random chance. That's what it's saying. It doesn't say what it actually is, what the difference actually is. It's just saying to say that there is no difference, there's only a 1% chance that I would get a difference of 2 if there truly was no difference. Okay. All right, so we'll stop there, and okay. So maybe not everything I said today made a whole lot of sense. Okay, and that's okay, because the first time you're exposed to hypothesis testing, it feels awkward. It feels weird. So we're going to pick up and we'll talk more about this hypothesis testing, the mindset behind it, and we'll work through some problems here. Okay. There's no homework assigned. Okay. But next week the lab will be due. Okay. So just turn in the lab, and it's meant to be easy. If you're having difficulty with it, just let me know. It's meant to be easy.